we usually think about medical diagnoses or, scientific breakthroughs with this expectation of total, absolute precision.
Oh, yeah, like structural engineering or something.
Exactly. It's like you fall off your bike, you break your arm, the doctor takes an x-ray, and well, there it is, the jagged white line on the black background. The doctor just points to the screen and says, there is the fracture.
Right. It is a very comforting way to view medicine.
Yeah.
It's binary. You are looking at a system where things are either broken or they're not. I mean, we desperately want science to be visible, to be neatly categorized into these absolute undeniable truths.
Right. But then you step away from the individual patient and into the world of medical research. You step into the massive, incredibly complicated machinery of how we actually figure out if a new drug works or if a certain chemical in the water supply causes disease.
And suddenly that pristine X-ray machine is just completely useless.
Yeah. Completely useless. You are looking at a diagnostic landscape that is incredibly murky because, before that doctor in the ER can look at an x-ray to diagnose your arm, someone, somewhere, had to run a massive study to prove that the x-ray machine itself actually works reliably on a population level.
Yeah, which brings us to the core issue.
Yes, which brings us to what I consider the ultimate Goldilocks problem of medical research.
The sample size dilemma. It's basically the invisible tightrope of all science.
Exactly. I mean, if a study is too small, it entirely misses the truth. The drug might actually cure the disease, like the effect is genuinely there in the real world, but because your sample size was too tiny, your data was just a blur. You missed it.
Right.
But on the flip side, if a study is too big, you are wasting millions of dollars, burning through years of precious research time, and ethically speaking, you're potentially exposing thousands more human subjects to experimental, unproven treatments than is strictly necessary.
It is the absolute definition of diagnostic muddy waters.
Mm-hmm.
I mean, navigating those waters, finding that exact perfect Goldilocks number of participants, it requires a very specific, highly mathematical map.
Which is hard to draw.
Very hard. If you get the numbers wrong at the design stage, your entire study is doomed before you even recruit your first patient.
So today, for this deep dive, we're looking at the invisible math that decides whether a medical breakthrough makes it to your medicine cabinet or, well, dies in a lab. We are extracting the core secrets from a specific biomedical research curriculum, specifically the concepts covered in Lecture 12.
Ah, calculating sample size and power.
That's the one. We are going to tackle the underlying truths of 30 specific test questions from this source material. But we aren't going to just read you a test prep manual. We're going to treat these questions as the raw data to give you X-ray vision into how clinical trials actually work.
And this matters whether you are a researcher designing a trial, a student preparing for boards, or honestly, just someone reading a headline over your morning coffee that claims, I don't know, a new berry cures heart disease.
Right, the miracle berries.
Exactly. When you understand the mechanics of sample size and statistical power, you can look at that flashy headline and immediately spot the structural integrity or the fatal flaws of the research underneath it. You stop being a passive consumer of science, and you start seeing the architectural blueprints.
Okay, let's unpack this. Before we can even start calculating a sample size, before we start plugging numbers into a formula, we need to understand the fundamental risks we are trying to manage.
We have to understand exactly when and how science gets it wrong.
Right. To do that, I want to use a courtroom analogy, because running a scientific study is essentially setting up a trial.
A very expensive trial.
Very expensive. So in the courtroom of science, the null hypothesis is the defendant sitting at the table.
Yeah.
And the golden rule of our system is that the null hypothesis is innocent until proven guilty. Now, the null hypothesis usually states that there is no effect, there's no difference, there is no association. The new drug you spent 10 years developing. The null hypothesis says it does absolutely nothing.
It's a sugar pill.
Exactly. That chemical in the water. The null hypothesis says it is perfectly harmless.
And as the researcher, you are the prosecutor. You desperately want to prove the defendant guilty. I mean, you're gathering a sample of data, your evidence, to try and reject that null hypothesis. You want to prove that the drug does work.
Right.
But, just like in a real courtroom, the jury is human. The data is incomplete. Mistakes can and will be made.
And those mistakes are statistical errors. The source material tests this concept relentlessly. Let's look at the first massive trap researchers fall into, which is the type I error, which statisticians call alpha. In our courtroom, a type I error is a tragedy. It is convicting an innocent person.
Exactly. The drug actually does nothing. It is effectively a sugar pill. But your study's data, by pure random chance, looked incredibly suspicious.
Like a fluke.
Total fluke. Maybe the 10 people who got the drug just happened to naturally recover faster.
Hmm.
So you look at the data, you point at the defendant, and you reject the null hypothesis. You declare the drug works. You convicted an innocent null hypothesis. This is your classic false positive.
There are a couple of specific concepts in the curriculum that hammered this exact point. They asked students to define a type I error. And the intuitive trap some people fall into is thinking it has something to do with not rejecting a false claim. But the absolute truth and the correct answer, you must know, is that a type I error occurs when the null hypothesis is rejected when it is true.
And another variation of that same concept asks for the definition of type I error in terms of probability. The correct answer there is that it is the probability of rejecting the null hypothesis when it is true.
So they're really just driving the same point home.
Oh, absolutely. Notice how they attack the exact same definition from slightly different angles. They really want to ensure you don't mix up the false positive with anything else. Type I error is alpha. It is crying wolf.
Wait, if this is a false positive, the real-world implications are terrifying.
Oh, they're catastrophic.
Right. You publish a paper in a major medical journal saying this new drug cures migraines. Everyone starts prescribing it. Millions of dollars are spent. Patients deal with side effects. And years later, someone realizes it was all just a statistical fluke. It was a type I error.
It is a massive deal in medicine. It's basically the genesis of the replication crisis in science. Because a false positive pollutes the scientific literature, it sends other researchers down expensive, totally useless rabbit holes trying to build on your fake discovery.
Wow.
This is exactly why the scientific community is so incredibly strict about alpha. Usually, we set our tolerance for this type I error at 5%. That is our standard alpha level, or a 0.05 significance level.
So we are explicitly saying before we even start the trial that we are willing to accept a 5% chance that we accidentally convict an innocent drug. We accept a 5% chance of publishing a false positive.
Correct. We draw a line in the sand and say, if the probability that our data is just a random fluke is less than 5%, we will reject the null hypothesis. We require the evidence to be that strong.
It's the scientific equivalent of beyond a reasonable doubt.
Precisely.
Okay, so that is the tragedy of the false positive. But what happens when we are so terrified of crying wolf that we miss the wolf entirely?
Ah, the false negative.
Right. What if the defendant actually is a criminal, but the jury looks at the evidence and lets them walk free? What if your new drug actually does cure the disease, but your study fails to prove it?
That brings us to the second kind of mistake, type 2 error, also known as beta. This is the false negative. The truth, out there in the objective universe, is that there is a real effect. The drug works, but your sample size was too small or your measurement tools were too noisy and you just failed to detect it.
The coursework is very precise about the phrasing of this, too. When asked when a type 2 error occurs, the exact right answer is that the null hypothesis is not rejected when it is false.
Let's break down that phrasing, because the double negatives can give people a serious headache.
Please do, because it's confusing.
Okay, so the null hypothesis is false meaning. The claim that the drug does nothing is a lie. The drug actually works. The defendant is guilty.
Got it.
But the null hypothesis is not rejected. You failed to throw it out. You let the guilty party go.
And there's another question that tests this by asking what is true about beta error. The correct answer they are looking for is that it is the probability of accepting the null hypothesis when it is false.
I am really glad we brought up that specific wording, actually, because I want to make a crucial semantic note here that statisticians care deeply about.
No. What's that?
Statisticians absolutely despise the word accepting when it comes to the null hypothesis. We prefer to say failing to reject.
Interesting. Why the distinction?
Well, in a real courtroom, you don't declare a defendant innocent. You declare them not guilty. You haven't proven their innocence. You just failed to prove their guilt with the evidence provided.
Ah, I see.
But in the context of many test questions in practical shorthand, accepting the null hypothesis is used to mean failing to reject it. You accept the idea that the drug does nothing, even though in reality it does something. That is your beta error.
So type 1 is crying wolf, type 2 is missing the wolf, and a type 2 error is its own kind of tragedy, isn't it? I mean, a life-saving treatment might be abandoned, funding gets cut, and patients miss out on a cure just because a study didn't have enough data to prove it worked.
Exactly. It's a silent tragedy. A false positive makes headlines and gets retracted later. A false negative just vanishes into a filing cabinet. Nobody knows what might have been.
Which brings us to the hero of the story.
Yes, finally.
Our goal isn't just to talk about our fears of making errors. Our goal is to successfully convict the guilty. We want our study to have the muscle, the sheer strength, to find a true effect if one actually exists in reality.
And that concept, the muscle of your study, is called power. Mathematically, power is incredibly simple. It is 1 minus beta. If beta is the probability of making a type 2 error, the probability of missing the true effect, then 1 minus beta is the probability of successfully finding it.
The curriculum attacks the definition of power from 3 different angles. Let's look at how they frame it. First, they define statistical power as a probability. The exact right answer is the probability of rejecting a null hypothesis when it is false.
Right. The null is false, the drug works.
Yeah.
And you reject the null, you successfully declare that it works, you have made the correct decision. You caught the bad guy.
They also test this by presenting a list of statements about the power of a study. And the one true statement you have to identify is that power can be defined as the probability of correctly rejecting the null hypothesis when it is false. They use almost the exact same words.
They do. And it's really worth noting why the trap answers are wrong. One trap suggests power doesn't influence sample size. That's totally backward. If you want more power, you need a much bigger sample size.
Obvious.
Another trap says power is represented by alpha. Now, alpha is type I error. Power is 1 minus beta.
And finally, they give a slightly more conceptual, less mathematical definition. They ask what we call the ability of a study to detect correctly the presence of an association. And the answer is simply power.
Think of power as the resolution on your TV screen.
Okay, I like this.
If you have low power, your study is like a grainy, pixelated security camera. There might be someone breaking into the house, but the resolution is so bad you can't tell if it's a burglar or a stray dog.
Right.
High power is a 4K ultra-high definition camera. If there is an association there, you're going to see it crystal clear. It is the sensitivity of your research instrument.
Wait, that raises an obvious question. If power is so great, if it's our 4K camera, why don't we just design every single medical study to have 100% power? Let's just make sure we never, ever miss a true effect.
Well, because to achieve literally 100% power, you would have to eliminate all uncertainty. The only way to eliminate all sampling uncertainty is to stop sampling and just measure everyone. Yeah, you would need an infinite sample size. You would have to test the drug on every single human being on Earth. Since we don't have infinite budgets or infinite time, we have to compromise. We have to decide what level of power is good enough for a standard analytical study.
And the curriculum explicitly tests this standard. It asks for the recommended minimum level of power for an analytical study. And the bolded, universally accepted answer is 80%.
80%. If we connect this to the bigger picture, an 80% power means that if there's a true effect out there in the real world, if the drug really does lower cholesterol, our study has an 80% chance of successfully detecting it and a 20% chance of missing it.
Meaning we are accepting a 20% beta error rate.
Correct.
Wait, hold on. We only accept a 5% chance of a false positive, our alpha, but we accept a 20% chance of a false negative, our beta. That means we are 4 times more willing to let a guilty defendant go free than we are to convict an innocent one. That means science is structurally biased against new discoveries.
You've just hit on one of the most profound philosophical realities of the scientific method. The entire architecture of medical research is inherently, intentionally conservative.
Wow.
It was built largely on the principle of first do no harm. The scientific consensus is that it is far worse for society to mistakenly believe a useless drug works and start giving it to millions of people than it is to mistakenly abandon a helpful drug.
So we protect the status quo.
Exactly. We demand overwhelming proof to change our minds. The 80% power convention balances the risk of missing a real effect against the harsh financial and practical realities of recruiting huge numbers of participants. If we demanded 95% power, the required sample sizes would skyrocket. Clinical trials would cost billions more, and medical progress might actually slow down because we couldn't afford to test anything.
That is fascinating. We are terrified of crying wolf, so we intentionally wear slightly blurry glasses.
That's a great way to put it.
Okay, so we've established the rules of our courtroom. We want our false positive rate, our alpha, to be low, usually 5%. We want our power to be high, at least 80%. Now that we know our goals, let's move into the kitchen. What are the actual ingredients that go into the mathematical recipe to calculate the required sample size?
To figure out how many people we need to recruit, we need to know a few things about the specific population we are studying, and we need to make some firm decisions about how precise we want our final answer to be.
Precision. That's a word people use every day, but in statistics, it has a very rigorous definition. The source material asks a true or false question. Precision is described as a measure of how close an estimate is to the true value of a population parameter. And the answer is true.
Precision is all about the width of your confidence interval. It's your margin of error.
Like in political polling.
Exactly like polling. Think about polling during an election. If a poll says a candidate has 50% of the vote, plus or minus 20%, that is incredibly imprecise. The true value could be 30% or 70%. It tells you almost nothing.
Right, it's useless.
But if the poll says 50% plus or minus 1%, that is highly precise. The narrower the margin of error, the higher the precision. But importantly, and this is the core of our Goldilocks problem, high precision is incredibly expensive. To get a narrower margin of error, you need a much, much larger sample size.
Right, because the more people you measure, the tighter your estimate becomes, the less the data bounces around.
Yes.
And speaking of data bouncing around, we have to talk about standard error, which is an ingredient that constantly gets confused with other terms. There's a true or false question that states, standard deviation of a sampling distribution is called systematic error. And the correct answer is false.
This is a classic terminology trap that trips up a lot of students. The standard deviation of a sampling distribution is called the standard error. It is a measure of random sampling variability. It is not a systematic error.
Can you break down the difference? Systematic versus random?
Absolutely. Think about weighing yourself on a bathroom scale. Systematic error is bias. It means the scale is fundamentally broken. It always reads 5 pounds too heavy.
I hate when that happens.
Right. But no matter how many times you step on it, no matter how large your sample size of weigh-ins, your average will always be wrong by 5 pounds. Math cannot fix systematic error.
Right. A formula doesn't know the scale is broken.
Exactly. Random error, on the other hand, is just the natural bounce of the universe. If you measure the height of 10 random people in your town, the average might be 5'8". If you pick a different 10 random people, the average might bounce to 5'9".
Just by chance.
Just by chance. That bounce happens simply because you only sampled a subset, not the whole town. That random bounce is quantified by the standard error. And unlike systematic error, we can fix random error with math. We fix it by increasing the sample size. The more people we measure, the smaller the random bounce becomes.
Okay, so we want high precision, meaning we want a small margin of error, which requires managing that standard error. What else goes into the recipe? The curriculum has a great summary question that asks which factors are necessary in sample size determination. The options include desired confidence level, desired precision, and the magnitude of the population variance. And the correct answer, all of the above.
Let's look closely at these 3 ingredients. The desired confidence level is tied to your alpha error, usually 95% confidence, corresponding to our 5% alpha. The desired precision is how wide you'll accept your margin of error to be, as we just discussed. But the third one, magnitude of the population variance, is arguably the most fascinating and problematic ingredient of all.
Variance, just how spread out the data naturally is.
Yes. Think about it intuitively. If you want to know the average number of arms a human being has, what is your required sample size?
1, maybe 2, just to be sure.
Exactly, because human arm count has almost 0 variance. Almost everyone has exactly 2. The population is incredibly homogeneous regarding that trait. So a tiny sample size gives you the exact truth. But what if you want to know the average income of a human being?
Oh, wow. That ranges from 0 to billions of dollars.
Exactly. The variance is astronomically high. If you only sample 5 people, you might accidentally include a billionaire, and your average will be wildly conically wrong.
You'd think everyone makes $200 million a year.
Right. So to accurately capture the true average of a highly variable population, you need a massive sample size to smooth out the extremes. The more chaotic the population, the more people you need to sample to find the signal in the noise.
That makes total intuitive sense. We need to know how chaotic the water is before we try to measure the depth. But let's look at what is not a statistical ingredient. There's a question that lists essential statistical considerations for sample size calculation and asks you to identify the exception. It lists precision, anticipated proportion, sampling method, and allocated budget. And the correct answer, the one that is not a statistical consideration, is allocated budget.
Now, any real-world researcher listening to this is probably groaning or laughing because in the real world, budget dictates absolutely everything.
Right. You can't run a trial if you can't pay the nurses or buy the lab equipment.
But the math formula does not care how much money you have. The formula is cold and unfeeling. If the formula spits out that you need 4,000 participants to achieve your 80% power, That is mathematical truth. If your budget only allows you to recruit 400 participants, the statistical reality is that your study is going to be severely underpowered.
You can't negotiate with the math.
No, you can't. You can't just plug $5,000 into the denominator of a sample size equation to magically make the math work.
Budget is the harsh awakening after the math is done. It's the reality check. Let's look at another question about the steps involved. It asks to identify the step that is not included in the estimation of sample size. The options are identifying the major study variable, deciding on desired precision, adjusting for population size, and adjusting for selection bias. The correct answer, the exception, is adjusting for selection bias.
This is a critical conceptual point. Steps like identifying your variable, setting your precision, and applying a mathematical correction if you are studying a very small, finite population, those are legitimate mathematical steps. But selection bias, that is a fundamental, fatal flaw in your study design.
Like doing a study on the average health of a city, but you only survey people at a marathon finish line.
Precisely. If you do that, your sample is horribly biased toward the ultra-healthy. No math formula in the world can fix that. You don't adjust for selection bias in a sample size formula. You prevent selection bias by designing a better study methodology in the first place.
So the formula assumes you did your job right.
Exactly. Sample size calculations inherently assume your sample is going to be representative of the population. If your underlying design is biased, the math is useless. Garbage in, garbage out.
Now, earlier you mentioned the magnitude of the population variance as a crucial ingredient, but when I think about that, I run into a logical wall, a complete catch-22. You're doing the scientific study to find things out about the population. How do you know the variance of the population before you've even done the study?
It is the great paradox of statistical planning. You need the variance to calculate the sample size, but you need a sample to calculate the variance.
So how do researchers solve it? The curriculum addresses this directly. It asks where population variance can be estimated from. The options are a pilot study, reports of previous studies, guessing, or both a pilot study and previous reports. The correct answer is both A and B, a pilot study and reports of previous studies.
We basically have to cheat a little bit to get the process started. First, we comb through the literature. Has someone done a similar study in a similar population in the past 10 years? If so, we could borrow their variance estimate. We stand on the shoulders of past research.
But what if your drug is totally novel? What if no one has ever studied this specific disease in this specific way before?
Then we have to conduct a pilot study. We run a miniature version of the experiment on a small handful of people, maybe 30 or 40 participants. The goal of the pilot study isn't to prove that the drug works. It's way too small for that. The goal is simply to get a rough preliminary estimate of how chaotic the data is.
Ah, I see.
Yeah, we calculate the variance from that small pilot group and then plug that number into our grand formula to calculate the true sample size needed for the massive final study.
And there's a true or false question that confirms this specific use case. It states, a pilot study can be conducted to get an estimate of the expected prevalence of the disease being studied to calculate the minimum required sample size. And the answer is true.
Yes. Whether you are estimating continuous variance for a mean average or an expected prevalence for a percentage, a pilot study gives you that initial puzzle piece so you can run your formula and get your funding approved.
You just touched on something really important there, measuring means versus measuring proportions. The curriculum makes a huge deal out of this distinction. Depending on what type of data we are measuring, the ingredients we need change slightly.
They absolutely do.
Let's look at the question regarding a single mean estimation. It asks which factor is not essential for calculating sample size for a single mean. The options are the need for statistical significance, assumptions about population standard deviation, precision, and significance level, and the correct exception is the need for statistical significance.
This one trips up a lot of people because the phrasing is subtle. Let's unpack why need for statistical significance is the odd one out here. When you are estimating a single mean, for example, you just want to know the average cholesterol level of adult men in Chicago. You aren't actually running a hypothesis test.
Right, there's no group A versus group B.
Exactly. You aren't comparing groups to see if a difference is statistically significant. You are simply trying to drop a pin on a map. You are building a confidence interval around a single estimate.
So you need the standard deviation to know the spread, you need the desired precision to know how tight your estimate must be, and you need the significance level like 95% to set your confidence. But you aren't testing for a significant difference.
Correct. Statistical significance is a concept deeply tied to comparing groups, to hypothesis testing, and to power. When you are just estimating a single number, the primary driver is precision, not power.
That makes perfect sense. A single mean is just finding a number, not proving a difference. Now let's contrast that with proportions. There's a scenario question about a cross-sectional study estimating the prevalence of a liver disease in a hospital. It asks what is not required for calculating the minimum sample size for this objective. The options are significance level, assumed prevalence, precision, and population variance. And the correct exception here is population variance.
This is a crucial mathematical distinction. When you are estimating a mean, like average weight in kilograms, you desperately need the population variance or standard deviation. You need to know how much weights fluctuate. But when you are estimating a proportion, like the prevalence of a disease, meaning what percentage of people have it, you don't need a separate variance number.
Why not? Doesn't a percentage have variance?
It does.
Yeah.
But for binary categorical data, you either have the disease or you don't want. The variance is actually mathematically locked inside the assumed prevalence itself.
Wait, really?
Yeah. If the prevalence is represented by the letter P, the variance is mathematically derived as P multiplied by 1 minus P. So you don't need to go looking for a separate variance ingredient. If you have the assumed prevalence, you automatically have the variance.
I see. Means need an independent standard deviation. Proportions just need the expected prevalence and the variance takes care of itself. Okay, here is where it gets really interesting. We have talked conceptually about all our ingredients. We know about alpha, beta, power, precision, and variance. Now it's time to actually bake the cake.
Time for math.
It's time to look at the math. But before we crunch the actual numbers, there is one overarching, highly counterintuitive rule about the expected effect that we need to establish.
This is the rule that breaks the brains of a lot of new researchers.
Let's read how the curriculum tests it. They provide a list of statements and ask you to identify the false one. The false statement, which is the correct answer you must select, is, as the magnitude of the expected effect increases, the required sample size increases.
That statement is completely backward. The truth is the exact opposite. As the magnitude of the expected effect increases, the required sample size decreases.
Let me try to construct an analogy here to see if I truly grasp this. Let's say I am an explorer, and my goal is to prove that an animal exists in my backyard.
Okay, I'm following.
If the animal I'm looking for is an elephant, well, that is a massive expected effect. The signal is huge. To prove the elephant is there, I barely need to look. I can just glance out my kitchen window. My sample size of observation can be tiny. One quick look and boom, hypothesis proven.
Right, a massive effect is obvious.
But if I'm trying to prove the existence of a very specific tiny gray mouse hiding somewhere in a giant chaotic city, the expected effect is minuscule. The signal is tiny. I can't just glance out the window. I would need to search thousands of houses, hire a team of hundreds, set up cameras everywhere. I would need a massive sample size. Therefore, looking for a larger expected effect requires a much smaller sample size.
That is a brilliant analogy. Let's translate it to medicine. If you are testing a miracle drug that reduces mortality by 90%, it saves almost everyone. The difference between the placebo group and the drug group will be so stark, so obvious, that you might only need 50 patients to statistically prove it works.
The elephant is in the room.
Exactly. But if your new drug only reduces mortality by 2%, a tiny whispering effect, you might need 10,000 patients to prove that the 2% difference isn't just a random fluke of the data. A massive effect shouts. A tiny effect whispers. You need a lot more microphones, a bigger sample size, to hear a whisper over the background noise of human biology.
That is so counterintuitive, but when you lay it out like that, it makes perfect sense. Big effect, small sample. Small effect, massive sample. Okay, with that rule established, let's look at how the curriculum makes students actually do the math. We'll start with estimating a proportion.
Let's do it.
There's a question about a researcher estimating the prevalence of surgical site infections in a hospital. We are given the following ingredients. The estimated proportion of infections is 10%. The desired absolute precision is 5%, and the confidence level is 95%, which gives us a z-value of 1.96. The question asks for the minimum sample size, and the options are 100, 138, 148, or 158. The correct answer is 138. How do we get there conceptually?
Let's walk through the mechanics of the formula without getting bogged down in reading a calculator aloud. The formula for a single proportion is a fraction. In the numerator, the top part, we multiply our confidence factor by our variance. Remember, for a proportion, variance is the expected prevalence multiplied by the remaining percentage. So 10% prevalence multiplied by the 90% who don't get infected.
Right, P times Q, so 0.10 times 0.90.
Exactly. And we multiply that by our confidence factor, our z-value, which is squared. For 95% confidence, z is 1.96, and squaring it gives us roughly 3.84. So the top of our fraction is just those three numbers multiplied together. It represents our desired confidence combined with the natural chaos of the disease.
Okay, so that's the numerator. What about the denominator, the bottom of the fraction?
The denominator is where the magic happens. It is our desired precision squared. The question asks for 5% absolute precision, which is 0.05. We square that number. Because 0.05 is a small decimal, squaring it makes it an incredibly tiny decimal.
And when you divide the top by a very tiny decimal on the bottom, the final number explodes upward.
Exactly. When you do the division, you get roughly 138.2. Since we can't recruit 0.2 of a patient, we always round up to ensure we have enough statistical power. So 138 is our minimum sample size. But I want to pause on why the precision is squared in the denominator.
Yeah, why is it squared?
This is the inverse square law of statistics. It means that if you want to make your estimate twice as precise, say, moving from a 10% margin of error to a 5% margin of error, you don't just double your sample size. Because the precision is squared, having your error requires multiplying your sample size by 4.
Wait, if I want to be twice as accurate, it costs me 4 times as much money.
Yes. And if you want to be 3 times as accurate, it requires 9 times the sample size. The pursuit of extreme precision is exponentially expensive.
That is a brutal mathematical reality. Now let's look at another math question that looks almost identical but contains a massive, fatal trap. It's about estimating the prevalence of antibiotic-resistant E. coli.
Ah, the relative precision trap.
Yes. The prevalence from previous literature is 6.5%. The researchers want a 95% significance level, but here is the trick: they want to estimate it with a 20% relative precision. What is the minimum sample size? The options are 1042, 1381, 6, or 600, and the correct answer is 1381.
This is where so many young researchers destroy their own studies before they even begin. Understand the difference between absolute precision and relative precision is critical.
Because, in the previous infection example, it asked for 5% absolute precision, and we just plugged 0.05 into the bottom of the formula. If I see 20% relative precision here, my instinct is to just plug 0.20 into the formula.
Right, and if you do that, your math will spit out a required sample size of roughly 6. That was option C. It is the trap answer. Think about the clinical reality. You are trying to measure a rare, dangerous antibiotic resistance that occurs in about 6.5% of people. If you go into the hospital and only test 6 patients, your study is a joke.
You won't find anyone with it.
Exactly. You will likely find 0 cases, and you will conclude the resistance doesn't exist.
So what does relative precision actually mean?
Relative precision means a percentage of the expected prevalence itself. The expected prevalence is 6.5%. The researchers are saying, we want our margin of error to be 20% of that 6.5%. So you have to do a preliminary calculation. What is 20% of 6.5%? It is 1.3%.
Oh, so our actual absolute margin of error, or absolute precision, is a tiny 1.3%, or 0.013.
Exactly. The researchers are saying, we think the true number is 6.5%, and we want our final estimate to be accurate within plus or minus 1.3%. Now, you take that tiny 0.013, you square it, and you put it in the denominator of your formula. Because that number is so incredibly small, when you do the division, your required sample size skyrockets to 1381.
That is a staggering difference. Misunderstanding the word relative takes your sample size from 6 people to almost 1,400 people. It's the difference between an afternoon project and a multi-year, multi-million-dollar grant.
Yeah, more importantly, it's the difference between a study that contributes valid, life-saving knowledge to the medical community and a study that is utterly useless and ethically questionable because it was statistically doomed to fail.
That is a fantastic breakdown. We have done the math for proportions. Now let's do the math for a mean. The curriculum has a question about estimating the mean D-dimer level among COVID-19 patients. D-dimer is a protein fragment in the blood that helps indicate clotting issues.
Right.
The ingredients provided are: standard deviation from past literature is 200. The desired precision is 50. The significance level is 95%. The options for minimum sample size are 62, 16, 31, or 248. The correct answer is 62.
The formula is a bit simpler here, right?
It is, because we are estimating a continuous mean, an average value like 500 nanograms per milliliter, rather than a percentage. We use standard deviation directly instead of P times Q.
So the numerator is just our confidence factor squared multiplied by our standard deviation squared.
Correct. Standard deviation squared is just the variance. So we take our z value of roughly 2, square it to get about 4. We take our standard deviation of 200 squared to get 40,000, multiply those together, and you have your massive numerator.
And the denominator is our precision squared. Precision is 50, so 50 squared is 2,500. We divide the massive numerator by the 2,500 denominator, and we land at roughly 61.4. We round up to ensure power, and we get 62 patients. This perfectly demonstrates how continuous variables require a fundamentally different mathematical approach than categorical proportions. But the core tension remains exactly the same. High confidence and high variance drive the sample size up. Allowing for a wider, sloppier precision drives the sample size down.
Okay, so up to this point, we have essentially been playing in a sterile, perfect sandbox of mathematics. We have assumed perfectly random samples, zero dropouts, and zero real-world chaos. But as you and I both know, reality is incredibly messy.
Oh, it's a nightmare sometimes. The basic formulas we just used rely on an assumption called simple random sampling. That means every single person in the entire target population had an exactly equal chance of being selected for the study, like putting 1,000,000 names in a giant, perfectly mixed hat and pulling out 138 names blindfolded.
But in public health and epidemiology, you almost never do that. If you are studying a whole country, you don't travel to 138 different random addresses spread across thousands of miles. Logistically, you usually sample by clusters. You randomly pick 5 villages or 5 city blocks, and then you interview everyone within those specific clusters. It saves a fortune in travel costs.
It's logistically brilliant, but statistically, it introduces a massive problem. And that problem is the loss of independent information.
How so?
People who live in the same village tend to be more similar to each other than to people in a randomly selected village across the country. They share the same water source, they might have similar diets, they face the same environmental pollutants, and they often share socioeconomic factors.
Right.
So if you survey the first person in a village, you gain a lot of new information. But when you survey their next-door neighbor, you're gathering somewhat redundant data. A sample of 100 people all clustered in one village does not give you as much diverse, independent statistical power as a sample of 100 people randomly selected from 100 different locations.
And this brings us to a concept tested heavily in the curriculum, the design effect, or DEF. There is a question that asks when a design effect of more than one needs to be considered. The options are cluster sampling, simple random sampling, stratified random sampling, or non-probability sampling. The correct answer is cluster sampling.
The design effect is essentially a penalty multiplier. Because cluster data is less efficient and contains redundant information, you have to penalize your study. You take your beautifully calculated baseline sample size and you multiply it by the design effect to get your true required sample size.
So it inflates the numbers.
Exactly. If your design effect is 2 and your basic math said you needed 500 people, you actually have to recruit 1,000 people to make up for the lack of independence in your clusters.
To hammer this home, the curriculum has another question asking the exact same concept in reverse. It asks for which sampling strategy the design effect is considered. And again, the bolded answer is cluster sampling. They really want students to mentally link those two concepts.
But it's also important to know when the design effect does not apply.
Right, there's a question about what is needed to calculate sample size for an analytical study using the simple random sampling method. The options are alpha, expected effect, beta, and estimated design effect. The thing you don't need is the estimated design effect.
Why? Because the mathematical design effect of a pure, simple, random sample is exactly 1. And what happens when you multiply your sample size by 1?
It stays exactly the same.
Right. So you don't need to consider it. It's already invisibly built into the baseline formula.
Now, here is a fascinating paradox about the design effect that the curriculum highlights. There's a true or false question that states, exact calculation of design effect for a study parameter can take place after study completion. And the correct answer is true.
It is true. Because the design effect depends on the actual statistical variance within your specific clusters versus the variance between the clusters. You can only run that complex math after you have gathered all the data.
Wait, if I can only calculate the exact multiplier number after the study is completely over, how am I supposed to use it to plan my sample size before the study begins?
That is the catch-22, and it is explicitly addressed in another true or false question. It asks you to evaluate the statement. The design effect should be calculated after completion of the study, and it need not be counted at the design stage.
And the correct answer to that is false. You absolutely must count it at the design stage.
Exactly. You must account for it during planning, and the way you do it is by estimating. Again, you look at historical data. For example, in global immunization cluster surveys, the World Health Organization often recommends simply assuming a baseline design effect of 2. You use that educated historical guess to inflate your sample size during the planning and funding stage.
And then you check your math later.
Yes. Then, after the data is fully collected and the trial is over, your statistician will calculate the true, exact design effect of your specific data. If the true effect was 1.5, great, you over-recruited and have extra power. If the true effect was 3, well, your study might actually be underpowered despite your best efforts.
It's like packing for a winter trip to a place you've never been. You estimate how cold it will be based on history, and you pack a heavy coat just in case. You only know exactly what the temperature was after the trip is over. But if you didn't pack the coat in the design stage based on an estimate, you would freeze to death.
A very apt analogy.
Let's look at a summary question about adjusting for the messy real world. It asks what we need to account for when estimating sample size for a cross-sectional study. The options are expected proportion, estimated design effect, population size, and all of the above. The correct answer is all of the above.
It brings all the pieces together.
Yeah.
You need your expected proportion to run the basic math. You need the design effect if you are clustering to adjust for redundancy. And you need the population size to apply something called the finite population correction.
What's that?
Well, if you are studying a super rare disease that only 500 people in the entire world have, you don't need a sample of 10,000. The math adjusts downwards when your sample starts to become a significant fraction of the entire total population.
But not everything requires a mathematical adjustment. The curriculum tests our boundaries here. It asks which of the following reasons does not require an adjustment to the calculated sample size. The options are non-response rate, finite population size, cluster design, and a hospital-based study. The correct answer is a hospital-based study.
And why do you think that is?
Well, the physical location of the study, the fact that it's in a hospital rather than a clinic or a school, doesn't inherently change the mathematics of probability. However, something like non-response rate, which was option A, absolutely alters the reality of the math. If your formula says you need exactly 100 people to reach 80% power, but you know from historical experience that 20% of patients will drop out of the trial or refuse to answer the survey or move away, you cannot just recruit 100 people.
Exactly. If you recruit 120 dropouts, you are left with 80, and your study is underpowered and ruined. You have to adjust for expected attrition. You have to over-recruit, maybe enroll 125 people, so that after the inevitable dropouts, you safely land on the 100 fully completed data sets you actually need. You adjust for attrition, you adjust for clustering, you adjust for finite populations. You do not adjust the math simply because the building has a red cross on it.
The final real-world adjustment we need to cover is confounding. In reality, biological variables do not exist in a perfect vacuum. Let's say I am doing a study to see if drinking black coffee causes heart attacks. I run my basic sample size formula, recruit the patients, and run the study. But I have to consider the reality that people who drink a lot of black coffee might also be more likely to smoke cigarettes, or sleep less, or experience higher stress.
Oh yeah, smoking is a massive confounder.
Right. So how does our basic mathematical formula handle these confounding variables? The curriculum has a true or false question on this. In general, sample size formula takes into account the crude association between exposure and outcome, as well as the confounders. And the correct answer is false.
The standard formulas we just spent all this time calculating using Z, P, Q, and D, they only calculate the crude, unadjusted association. The formula is entirely blind to confounders. It assumes a pristine, unconfounded universe where the only difference between your two groups is coffee consumption.
But we know that pristine universe doesn't exist. We know we are going to have to use complex statistical models like multiple logistic regression at the end of the study to untangle the coffee from the smoking from the stress. And those complex models require more data. So how do we fix our sample size calculation at the very beginning to account for the complex math we will do at the very end?
There's a final rule of thumb provided in the curriculum.
Yeah, a true or false question states, for each confounder or variable added in the study empirically, 10% increase in the sample size should be made. And the correct answer is true.
This is a highly practical, deeply embedded rule of thumb in epidemiology, the 10% rule. If your basic formula says you need 300 people to find a crude association between coffee and heart attacks, but you know you need to mathematically control for age, sex, and smoking status in your final analysis, that is 3 confounders. You should empirically increase your sample size by roughly 10% for each one, so you add 30% more participants, bringing your total to 390.
Why do we do this? Because every time you slice the data to control for a variable, you are thinning out the herd.
Exactly. If you want to compare coffee drinkers to non-coffee drinkers, but only among the 50-year-old men who smoke, you are looking at a very small subgroup of your total sample. Adding that 10% bulk for every confounder ensures that when you slice and dice the data at the end of the trial, you still have enough statistical power within each tiny subgroup to find the truth.
That is incredibly practical. Add 10% for every variable you want to control for. Well, we have covered some serious conceptual ground today. Let's recap the journey we just took through the invisible architecture of medical research.
It's been quite a ride.
We started in the courtroom of science, defining our deepest fears, the type I alpha error, where we cry wolf and publish a false positive, and the type 2 beta error, where we tragically miss a real cure. We established that power is our ability to successfully convict the guilty, aiming for an industry standard of at least 80%, which revealed that science is intentionally conservative.
From there, we moved into the kitchen and gathered the ingredients for our statistical recipes. We learned that the magnitude of population variance applies to means, while expected prevalence mathematically locks in the variance for proportions. We saw how precision dictates the tightness of our estimates, and why standard error is about random bounce, not a broken scale.
Then we actually crunched the numbers. We learned the golden counterintuitive rule. Looking for a massive elephant requires a small sample, but looking for a tiny mouse requires a massive one. We explored the devastating trap of relative versus absolute precision, seeing how a simple misunderstanding of the word relative could doom a study of antibiotic resistance by under-enrolling by over 1,000 patients.
And, finally, we took our pristine mathematical sandbox and threw it into the messiness of the real world. We learned we have to multiply our sample size by the design effect to penalize ourselves for the redundant data in cluster sampling. We learned to plan ahead for the inevitable human reality of dropouts, and we learned to add a 10% buffer for every confounding variable to ensure our statistical models don't completely collapse when we finally analyze the data.
We didn't just read 30 multiple-choice questions. We extracted the absolute truths behind them. So what does this all mean for you, the listener? It means that the next time you are scrolling through the news and you see a headline screaming, "New study proves coffee cures everything," you don't just take it at face value. You don't just accept the X-ray. You can look at the methodology.
Ask the hard questions.
Exactly. You can ask, was the sample size actually large enough to have the power to prove this? Or was it just a tiny pilot study of 6 people? Did they account for the design effect? Did they adjust for dropouts and confounders? You now have the intellectual tools to separate statistical noise from actual scientific truth.
It truly is X-ray vision. But as we close, I want to leave you with a provocative thought. Everything we discussed today treats sample size calculation as a static event. It is a hurdle you clear before the study begins. You calculate a fixed number, say 1,000 patients, and you march toward it regardless of what happens in the middle of the trial. But right now, at the absolute bleeding edge of clinical research, artificial intelligence and machine learning are beginning to infiltrate trial design.
Okay, where is this going?
Well, could we see a future where algorithms dynamically adjust sample sizes in real time? Imagine a trial that doesn't have a fixed target of 1,000 patients. Instead, the AI constantly monitors the accumulating variance and the emerging effect size with every single new patient that gets enrolled.
Whoa.
If the drug is an absolute miracle, the elephant in the room, and the variance is surprisingly low, the AI could automatically halt the trial early at just 300 patients, declaring victory. This would save millions of dollars and get life-saving drugs to market years faster. But if the data is bouncing around wildly and the variance is huge, the AI automatically keeps the trial open, expanding the required sample size dynamically until that golden 80% power is definitively achieved.
That is a wild thought. The courtroom of science running in real time, constantly recalculating the size of the jury until the verdict is statistically unassailable? We started this deep dive by comparing medical research to an X-ray machine. It seems the X-ray machine of the future might just mathematically calibrate itself. Thank you so much for joining us on this exploration of the invisible math that runs the medical world. We hope you feel a little more powerful and a lot more precise. Until next time, keep questioning the numbers.
Goodbye, and keep exploring.